Okay, let me know if anybody's having trouble accessing the link to the collab. I'll present it here. All right, can everybody see what I'm presenting? Yeah? Yep. Okay, sounds good. All righty, so is everybody able to access the link, no problem? Any issues, just put it in the chat or raise your hand or something, and I will try my best to make sure to fix it. Okay, so this is, this tutorial is basically just going to be, or hands-on exercises.
Sorry, what is the name of the, I cannot find it in the shared directory.
On the shared directory here, yeah, I can put it there. The link to it.
I just pasted a link into the chat.
Oh, okay, yeah. Okay, got it. Thank you.
And then I'll put it in the shared directory after we're all done today.
Okay, thanks.
Yeah, no problem. Any other issues? Anybody else having trouble finding it? Okay. All right. So today's hands-on exercises are just going to be about importing cells, externally defined cells into NetPyNE and using those, kind of manipulating those, changing the parameters that define those cells once you've imported them. Potentially, if we have time, we'll get into using them to develop a network. So let's just get started here. Okay, so the first thing we're going to need to do is we're going to need to clone the repository that I made on GitHub that contains all the mod files and all the cell files that we'll be using. Let's see. So the first thing will be to, and let me know if anybody is falling behind or if I'm going too slow, anything like that. So the first thing, I just want to make sure that we are, which directory we're in. So it shows you the kind of the file system over here on the left. Yeah, okay, so this is the content directory, at least that's the default directory that Colab has been bringing me to. I assume that's the same for you guys. So we want to start there and just make sure that's where we are. And if we're not, just put in this command, just change directory to cd into content to make sure we're all starting from the same place. Okay, and then again, just to make sure, just print the working directory. You should see that we are in the content directory. So the first things that we'll need to do should probably be pretty familiar. So we're going to need to just make sure that Neuron and NetPyNE are installed, and we're going to be importing a few modules. So we're going to be importing Matplotlib and OS for a reason you'll see in a second, and also JSON so that we can make sure that we can import cells of that file format. So just go ahead and run those commands. Let me know if anybody runs into any issues with that. Okay, everybody good so far? Okay, see something in the chat. Okay, I see Json. Okay. All right, so then the next thing would just be to make sure that we have Matplotlib able to put things, inline. So if we make any plots, we'll be able to see them usually. Okay, and then so this line is just if you're ever rerunning this code, this is going to go ahead and look within your directory, see if this repo already exists, and it's going to remove it. That way, when you clone it, you're not, causing any issues. So I just put that in there for anybody's future benefit. If you are running this again in the future, that should hopefully clear up any errors there. Any questions so far? Everybody with me? And just to keep in mind, also, this is something I noticed when I was making this files section here. It seems like it takes a little while to catch up. So this may have actually already run, but then sometimes I've noticed if you click this and then click it again, sometimes that helps. So just be aware that this is not the fastest in terms of updating. Okay, and so the next thing we're going to need to do is we're going to need to clone the repository. So let me know if any of you have any issues with that. So this is just going to clone in the Git repository that I made. It's going to contain all the mod files and all of the cell files that we'll be working with. And I assume by now, and maybe I shouldn't be assuming, but just any questions on mod files and what those do, what we use them for? Any questions there? Yeah, so the mod files they're basically just, they specify things like channel mechanisms. They give us, say, the time constants of certain currents and things like that. And so they are necessary for being able to, insert channel mechanisms into a cell model so that, we can model it. And let me know, was everybody able to clone the repository? Any issues there? Okay, it's fine. Okay, so then we're going to, again, it's not catching up here, but should, yeah, there we go. Okay, so next thing, I just want to make sure that we are all in the repository. So it's called cells NetPyNE2021. So just changing directory into that. And again, just ensuring that that's where we are by doing print working directory. Okay, so the next thing we're going to need to do is run the neuron IV model command. And so that just is going to compile the mod files. And we should see, once that's completed, the creation of this x86-64 directory, like I put up here. Let me know if anybody has any issues with that.
Erica, can I make a question?
Yeah, sure.
And okay, let me see. And in the line CD cells NetPyNE, why we don't use the exclamation point?
That's a very good question that I don't know the answer to, because when me and Joao, one of the other tutors, when I was having him run this earlier, when I did have that in there, it was not working. And it wasn't working for me, wasn't working for him. I didn't delve into it. I just took off the exclamation point because that's what worked. But I don't have a good answer to that. If anybody knows, I would be curious. I planned on just giving it a Google later on. All right. So,
thanks.
Oh, IPython accepts CDA. Okay, yeah, that makes sense. All righty. So,
I had a quick question about what we just did. So it looks like we're translating all of these mod files into, it looks like .c files.
Mm-hmm.
So why do we have mod files instead of just .c files?
So I'm not a C programmer, so I don't know if I'm going to be able to answer this to the most satisfying way. But so Neuron, essentially, and you guys have been working with Neuron, right? So NetPyNE is kind of this overlay on top of Neuron. And so Neuron is the software that we use usually to define our individual cells. And so those are in Hoke, or it was originally in Hoke, which I believe is a kind of a C-esque language. And so there is we just compile these mod files, and I'm sorry, I'm not a C programmer. I'm a nurse.
You have to compile them yourselves because they have to be compiled on your individual machine.
Yeah.
So a Windows machine is slightly different from a Mac, is slightly different from Linux. And so everybody has to compile them for their own architecture.
Okay.
Wow. Yeah. So just to give you guys some background, I am a neuroscientist by training and started doing computational stuff when I joined the lab. So thank you, Joe, for stepping in there. Let's see. Okay, so yeah, so we
yeah, I'm sorry, may I ask something?
Yeah, please.
Sorry, I just joined. Could you tell me where to take this notebook?
Oh, sure, yeah. So we are at the line git clone.
Yeah, I mean, the whole
There's a
notebook.
link to the collab in the chat of this meeting.
Okay. Okay, in general?
Yes.
Okay, thank you.
Yeah. Alrighty. Okay, so we've gotten up to the part where we've cloned the directory into our file space here. Let me know if anybody's having any issues doing that. So yeah, what we should see.
Here's the question.
Yep.
So right now we are going to your GitHub, and then there's a folder which has all these files. But if we download all those files to our own computer, how to do that?
So you can, so git clone is essentially, I mean, you can do it actually on your local machine as well. So if you were to open up, a terminal, go to the command line and run that same command, just git clone and then, that URL, that will actually clone that directory onto your computer. So then you will have a copy of that repository that you can use locally.
Okay.
So that can be very helpful, very useful. And so, yeah, you could also, I'm not sure if you're able to do that here, I haven't been trying, but I suppose you could probably just literally individually download these files if you didn't want to make a copy of the repository per se and just kind of wanted to have your own thing. That would be fine too. But yeah, repositories are very useful because it allows for easy collaboration and things like that. You can make your own branches and work on things separately, kind of merge back in with what other people are doing. So they are very useful for software projects. But for this, you know, if you wanted to download the files individually, you could feel free to do that. You could also clone this onto your local machine as well.
Got it.
Yeah. All right. Any other questions with respect to this? Alrighty. And feel free if there are. Okay, so then, yeah, we changed directories. We want to make sure that we're in this directory. We want to make sure that we've compiled the mod files. So that looks like it went well. Anybody have any issues compiling mod files? Okay. So I assume that you all have NetPyNE and everything installed. Again, maybe you shouldn't be assuming, but you know. So the first thing we're going to do is, and I believe you've encountered this from your other exercises and stuff, we're just going to set up a NetParams object. So we just run this. So from NetPyNE, we're importing specs, we're importing sim, and we're establishing NetParams. So this is an object that's going to store all of our network parameters. Okay, any issues there, just let me know. And then, so the first thing that we're going to want to do, so basically this section, kind of 2A through 2D here, what we're doing is we're just going to import externally defined cells. And so on the left here, you can see there's several mod files, but then there's a couple files that are different. So there's these .swc files, there's this .json file, there's this .hoc file, another .swc file, and there's a .py file. So all of these are externally defined cells, and you can open any one of them to get a sense of what they look like. And I believe I saw Salvador going over a .py file that defines a cell. These SWC files, so again, if you guys already know this, I apologize, but so those are generally used for morphologies, so for more complex morphologies. Tomorrow, I'll be talking to you about just kind of the broad overview of steps that we take to build a data-driven multi-scale model. And so for people who are interested in using detailed morphologies of cells, so you don't want to use this kind of simple, you know, 2 or 3 compartment ball and stick model type of thing, and you want to be modeling, you know, stuff about the proximal and distal dendrites and things like that, then you're going to want some more complex morphologies, and that usually comes in the form of these .swc files. So I just wanted to go over how to import those, how to import this, and also .hoc files, which are kind of, you know, neuron based, and then these .py files, which are, you know, in Python. So the kind of the weird one first. So we'll go through the JSON one first. So netparams, it's just this command right here. netparams.load cell params rule. So you may have encountered import cell params. So I believe that only takes swc.hoc and .py. Not .json files. At least it gives me an error every time that I've tried to do that.
Yeah, I'll update that. I'll add that to my list.
Yeah. So good to know that it's not somehow my doing, Joe. That's a relief. So yeah, so if you do have a .json file, and so you may see this say, if you're looking through some of our models of cortical columns, like motor cortex, auditory cortex, oftentimes we will have saved cell parameters and cell rules into a .json file. And so if you want to be able to use that, it's pretty simple, just netparams, load cell params rule. You give it a label, and then you enter the file name. And any issues doing that, anybody running into any errors, let me know. And one way we can kind of test to see if this worked, and we'll go through this at the end, but we can actually just do it now. Add a line here. If we want to say netparams.cellparams now, and just run this and see what we get for an output. And so we see that this cell type got loaded in, and we can see all the different characteristics, the different parameters that go into defining this cell type. And a more succinct way, so this is a dictionary. Hopefully most of you guys are familiar with Python dictionaries. If not, there's plenty of tutorials online, and they're relatively easy to get the hang of, and NetPyNE uses them a lot. We can just look through the keys of this dictionary, and it'll show, okay, so one type of cell is loaded into NetParams, and that's this TC reduced. TC in this instance stands for Thalamocortical. This is a Thalamocortical cell model that we are using in our auditory cortex model, just for more context there. Okay, so any questions on that file format?
I have a question.
Yeah, sure.
So you upload this JSON file where you define a lot of parameters regarding the cells, right? But if I have the same parameter file but in a HOC file, would that work in the same way?
Yeah, so the syntax is going to look a little different. We will be actually importing a HOC file here, but it's essentially, and we import it in a slightly different way with import cell params, but the idea is basically the same. So, you know, when we have this, look, we can see that it's just going to, this dictionary is going to remain pretty much the same no matter if we import it from a .json, or a .hoc or a .py. You're going to see that there's these conditions associated with it, where, you know, what kind of cell model and what kind of cell type, the different sections, so Selma, and we're going to see, you know, different electrophysiology things, you know, like what type of ions are in there, and then, you know, what kind of channel mechanisms. So it's essentially going to look pretty much the same, but how we import them is just going to differ a little bit, and the syntax within each file is going to be a little different as well. Does that answer your question? Sorry.
Yes, perfect.
Okay. Alrighty, so then let's see. So next, let's just take a look at a detailed morphology file. So this is one of our .swc files, and that's this one here. And so here we can see that the way to import that's a little more wordy, but we have NetParams, and the command is .import cell params. And so we give it this label. The conditions associated, we're going to have to specify the cell type and the cell model. And then we give it the file name, and then we can call the cell you know, what we would like, or I believe actually in this case it might actually be defined. But so let's give this a run. Does that work for everybody? I believe SWC files are only able to be uploaded in the latest version of NetPyNE. I think I had to upgrade mine in order to make that happen. So if anybody's having any issues there, that might be the reason. I believe that was the reason I was having trouble. So let me know.
It's a pretty recent addition, yeah.
Okay, yeah. So if anybody's having trouble with that, it might just be the version of NetPyNE. Okay, and so again, we can just see now if we want to look at, you know, what is in the cell params of our NetParams object. And now we can see that this one has been added. So we have the Thalamocortical cell, and we have this more detailed SWC file as well. All right, so the next one, a HOC file. So this is going to use the same command as the one above here. So import cell params, same things. It has a label, some conditions that include the cell type and cell model. You give it the file name, cell name, and we also have this thing, the import synaptic mechanisms. This can be true or false, depending on, you know, whether or not there are synaptic mechanisms specified in your file and whether or not you want to import them. And you can set that to true or false, you know, depending on those things. So you can go ahead and give that a run. And again, we can check that here to make sure that it actually got in to our dictionary. Okay, and so now we can see the Thalamocortical cell, the cell from the SWC file, and now the cell from the HOC file. All right, any issues with those so far? Okay. All right, and so lastly, we are going to import something from a Python file. And so that's going to be this reticular cell. This is also a cell that we are using in our auditory cortex model, or it's not in the cortex, it's actually in our thalamic reticular portion of the auditory thalamocortical model. And so this is just the Python version of the cell that we are using. Feel free to open it up. You can take a look at how the cell class is defined, things like that. Again, I believe Salvador went over a similar Python, a way of using Python to define these cell classes and stuff. So you can see another example by opening this up if you'd like to. Again, same thing, import cell params. There's a label, conditions that include the cell type, cell model. You have the file name, cell name, and again, import synaptic mechanisms is going to be true or false depending on what we just talked about. You can go ahead and give that a run, and we can again just make sure that that made it into our cell params dictionary, and it looks like it did. So we have the thalamocortical cell, we have our the cell from the SWC file, the cell from the Hope file, and we also have this reticular cell from our Python file. Any questions so far?
Yeah, I just had a question to make sure I understand these. So the .py file, I looked at it, it's a class with like a cell class and then like an SRE class that like references the cell class. And so if we weren't using NetPy, but we were just using Neuron through Python, you could just, I guess, like import that as a module and then just like call SRE and like make an instantiation of that cell. Is that how you would use that outside?
Yeah, I believe that's correct.
Yeah, sorry, you broke up a little bit at the end there. I think my connection got bad. You said, yeah, if you just wanted to use this, correct me if I'm wrong, in Neuron with Python, and would you just be able to just import this and use it?
Yeah.
The module? Yeah, I believe that that would work. Again, I can go ahead and try it. You go ahead and try it, and if there are some particularities to work out, as you know, as there sometimes are, feel free to go ahead and post that on the Ask Tutors channel, and we can work through that. But again, yeah, this should be flexible enough to use in both, you know, Neuron and in NetPyNE.
Okay, and I just had one other question. So with the Hawk file, the Hawk file, it's basically giving similar instructions. It's just that it's more similar to like a function rather than a class, right? So when you load it, it's sort of the same, but slightly different. Like what they were writing in Hawk is more of a function. I think that's what a template is or something, right?
Yeah, so Hope uses a template instead of a class, but I think it's pretty similar.
Yeah, yeah. So it should be defining, you know, the same types of things as you would in Python. Syntax is going to look a little different. Because again, Hope is mostly asked than Python.
Actually, do you have a question on that? I've got a morphologically realistic biophysically detailed model, but I'm having a lot of trouble because it's in Hawk and I'm having a lot of trouble turning it into a template.
Okay.
And I was wondering if you had any workarounds in order to get it into Python and into NetPyNE if I'm having a lot of trouble getting it to run as a template.
So that's probably going to depend on the nuances or particularities of whatever file you've got going on. I'd be happy to take a look at it and see if there is, you know, something convenient that we can do to mitigate those difficulties. It can definitely be a pain trying to, you know, take these disparate formats and, you know, use them, you know, in these different softwares. So feel free to message that or send it to wherever, and we can try to take a look at that and see if we can. So you have an SWC file for the morphology, and you also, so how is the biophysically detailed stuff instantiated? Like, what is that?
I think that might be part of my problem. At some point, they took the SWC file, made it into a Hawk file detailing the geometry. Then they have separate files doing cell setup and things like that.
Gotcha. Okay.
And I think the Hawk file, when I try and call it in a template, is not happy with me.
Okay. Okay. And how are you doing? What is the process that you're using to do that?
When I put it in the template, I just have template, open file, my cell Hawk, and it's just not. It's weird because if I make it a template and run it once to make one cell, it's fine. But if I try and make it more than one cell, it gets fussy with me. It won't work, and I'm not quite sure why. And I was wondering if maybe since this is a 3D morphology, if I'm putting one cell right where another cell is, because it gives me a segmentation violation, but only if I run more than one cell.
Okay, yeah, so the PT, you may see like PT3D scattered throughout some of this, so that is going to be specifying kind of the 3D aspect of the cell. Is this, does this model happen to be on ModelDB or anything like that?
A previous version, yeah.
Okay, yeah, so if you want to send a link over, maybe you can just kind of take a look at it and see if, you know, I'm able to give any more helpful advice. Yeah, I apologize for not without being able to see the files. Sometimes I might not be able to say anything too intelligent about it. All right, cool. So you sent the link over, so I will take a look at that after the class is over. Okay. Yeah, so so you got some mod files here. Got a Hope file here. Okay. Yeah, there should be, this looks this looks complicated, but doable probably in terms of, you know, using this in a network. All right, so thanks for sending that, and I will definitely take a look at that, and feel free to send it to the channel as well, you know, if anybody else has any input. Let's see. All right, so then I just have a quick exercise here. Import, so there's another SWC file in here. So this is from something called neuromorpho.org. And let me just post the link here in the chat. So neuromorpho.org, it's a great resource for being able to find morphologies of different types of cells, if that's something you're looking for. If you go to that link, you'll be able to see that you can browse by species, by brain region, by cell type, and you can find and download detailed morphologies in terms of SWC files, you know, and use those in the manner that we've shown here, where you can import them. So if anybody's looking for that, and if that's of any use in your future projects for this, that can be definitely a great resource. So I just found a GABAergic hippocampal neuron, you know, from a mouse. Just nothing in particular, no particular reason for it. But so yeah, I found that, downloaded it, and so there's just a you know, little opportunity to try and import that on your own. So go ahead and give that a try and see if there's any questions there. Give that about a minute till 5:28 or so, 5:29. Or if everybody's done, you can just tell me in the chat. So I'll give it just another 30 seconds or so. All right, so I guess we can start going over the solution, unless anybody wants me to hang on a minute. Let me know. If I get no objections, then I will I'll just plow ahead. Okay, so as you can see, we're going to be using the import cell params command like we did for the others up here. We need to give it a few things, as we discussed: label, conditions. We need to give it the file name, and then cell name. So what I used for the label, I used this, just mouse hippocampal SWC, just to give us something. Cell type, said this was a hippocampal cell. Cell model, I said similarly to some of the SWC files above, I just called it Hodgkin-Huxley 3D. It doesn't have any Hodgkin-Huxley mechanisms in it. That's something that we can add later on that we'll go into, but I just called it that. The file name, as you can see from the directory, is just the file name, mouse GABA hip.swc, and then I gave it, this is a cell name. So then we can go ahead and run this. And again, if we want to check to make sure that it made its way into our cell params dictionary, we run this, and we can see that, okay, so we have our thalamocortical cell, the previous SWC file that we looked at, the Hoag file, we have a reticular cell from our Python file, and then we also have this other mouse SWC file that we got from neuromorpho.org. All right, any questions on that or on neuromorpho or anything else?
Can you, what's the significance of calling the cell model HH3D? Like, what does it point to that's of use to us?
So it will be of use later. So that is something that, so you can see it's in conditions. So when we are, say, defining a population based on the cells that we've entered. So if we're creating a population of cells in NetPyNE, we'll do netparams.popparams, and then we'll say, okay, we'll give it a cell type, the number of cells, the cell model, things like that, to say, okay, which cells that we've defined in cell params are we going to use to create this population. So those are kind of things that, right here, it doesn't necessarily point to something specific, but later on we'll be able to kind of hook onto that to make sure that that's the particular cell that we're using. That make sense?
Can I make another question?
Yeah.
There is no problem of using 88-3D underline CWC, and in the other one that is also a CWC 88-3D only, or there is some problem in using different names?
It shouldn't be a problem because they are all distinct. I was just, you could definitely call this something else. This was just, this was actually a first pass, and then I realized that later. I was like, oh, they are sort of similarly named. So if I was actually making a network model, I would probably do something more distinct, just for the sake of clarity and documentation and stuff like that. But they are syntactically separate, so it should be fine.
Okay,
we'll be able to tell the difference. Yeah.
So in other words, like whatever you write for what the cell model name is not something that is being like recognized as a specific like template for something else to happen, right? So like in the sense, for example, where cell model, you want to write cell model, and that's recognized as like something particular, but like HH3D, that could just be anything. It's not something that like has to be a specific like set of options, or it'll run an error. I think that's
okay. Yeah, you're saying like, is there a predetermined like list of things of like type
so like it's like color equals
gotcha, yeah,
R. It's like it needs to be R, not R.
Yeah, no. Yeah, so it's not a thing where it's going back and it's referencing some pre-existing list, like color or something like that. Yeah. So like in Matplotlib or whatever. Yeah, so that's just something that you can determine there, and then we'll use it later on. But there's no restrictions like the kind you're talking about. Yeah.
Okay.
Yeah, I'm sorry. Just to be sure, the cell model is arbitrary, right? The file name is obviously the file name.
Correct. Yeah.
And the other fields, label, cell type, cell name, which of those are arbitrary? Which of those should correspond to something?
Yeah. So that's definitely something that because some of them are arbitrary and some of them are not, for sure.
So what I feel is these are dictionary keys. So anything on the right-hand side and anything on the left-hand side can be different. Anything on the left-hand side should be fixed, and anything on the right-hand side should be like changeable.
So left and right of what? I just want to make sure.
So for example, you have written cell model that is fixed, but something on the right-hand side, HH3D, can be changed.
Yeah, that's correct. So I mean, these keys are definitely fixed, and some of these values are changeable. Like a cell model, I could have called this something else if I wanted to. I could have called this just mouse. I could have called this underscore mouse, and that would have been fine. But like Nikita's saying, the file name is not. Okay. So the cell name. So for example, if you look at sre.py, so again, I'm not Joe, jump in here if you want, but so the class name, I always use the cell name as the class name if that's defined in a .py file. And the label, I believe, is arbitrary. For the cell type, well, that depends. If it's a JSON file, that's already going to be saved. Let's see. So the cell model is arbitrary. The file name is not arbitrary. Right. The cell name the cell name and the label, I do believe, are arbitrary as long as they're consistent. But Joe, if you have anything to contradict me.
Sometimes the cell name is important, I think, because it's used to, it's the name internal to the file, which creates the class or creates the template, the class or template internal to the file. Because NetPyNE has no way of knowing what a file calls the thing that makes the cell.
Yeah. but then I think sometimes for the SWC files,
they don't have, they won't even have anything in an SWC
right.
file, so it won't matter. That's arbitrary for that one.
Yeah. So it's going to depend on, if you're just importing a new, morphology like this one, this is going to be arbitrary. For something like a .py file, I would use the name of the class that is defining the cell. So yeah, so again, it's going to just kind of depend on, which type of file you're importing and what information is specified in there.
Yeah, what about label and cell type?
Label and cell type. Okay, so label, I believe, is arbitrary. And then cell type, I'm trying to think of an instance where it wouldn't be, again, like for something like an SWC file, the cell type, you can declare that. So you can see up here, this is quote, a pyramidal cell, PYR. Same thing with this one. So they don't need to be distinct from each other. They can also, these are both arbitrarily given. This isn't defined in the SWC file. The cell type here, so the cell type, so in this .json file, for example, if you open that up and you look, the cell type is declared already as TC. So I would, in all future things, I would say the cell type is TC, but that's going to get imported with that .json file. In the other ones, in the hoke files and the .py files, I am not entirely sure if it's always arbitrary.
Okay, thank you. I think I got it.
Yeah, no, it can be a little bit. It can be a little bit tricky, and that's definitely something that I kind of went around and around with when I first started. It's like, okay, which of these is already in the file, and which of these is something that I have to declare? So looking at examples is how I always kind of sorted that out.
I think you can just change my name, and then if it's running, so it's okay. I failed. Just try.
Yeah, that's true. This is a low stakes game, so you can change stuff and change it right back. If it doesn't work, change it to something new. So any other questions with those imports? Alrighty. Okay, so then I just wanted to be able to go over how to kind of explore and manipulate the cell parameters that are in these files. So, in some of the other stuff that you guys have probably looked at and that I've seen from the other tutorials and stuff, you're defining these cells as you go along, versus in this, we're kind of importing things from, say we're on ModelDB, which I'm not sure if you guys have been to yet or made an account, but so ModelDB has, a ton of different cell models, and say you are like, oh, well, I don't feel like making a layer 4 spiny stellate just, de novo. I would like to import it from somewhere else. You're going to want to be able to go through and see, okay, what kind of channel mechanisms did they put in this cell? How big is it? Do I need to change this Selma size because they used a monkey and I'm using a mouse? So you want to be able to go through and explore all those parameters and make sure that they are what you want and know what you have to change if something isn't working, stuff like that. So thankfully, this is all just in the dictionary like we talked about. So you can go ahead and see, like, this is the command we've been running. So from here, if you guys want to explore around in the dictionary, I put a little exercise here just to find the geometry, so the length and the diameter of the soma compartments for each of the above cells. And so I'll just give you guys a few minutes. Feel free to ask any questions. I'll give you maybe to like 5:41 just to, and then we'll check back in to see how you guys are doing with that. Okay. How's everybody doing? Do we want to just go over the... So anybody find the length and diameter of the thalamocortical cell soma compartment?
.96.
Yeah, so the length would be 96 and the diameter is also 96. Any questions on how that was located? No. Okay. So yeah. So basically, you know, the way if you're not sure what is in something, you just look at the keys. Say, oh, okay, I want to look at the thalamocortical cell. And again, you can just kind of look through this dictionary and explore around, and you can see, oh, okay, well, the sections, I know that, you know, we're going to have, and I'll just take a shortcut here. You know, got the soma. What kind of things do we got? Okay, we have the geometry, the ions, the mechanisms, topologies. We have the voltage that it starts at, and we have the normalized weight, which doesn't come into play right now. But so we want to look at the geometry. And we can see, okay, so it has all of these different features. And so we are looking, you know, just for right now at the length and the diameter. But NSEG is going to tell you the number of segments that this has. CM is going to be the capacitance, and then the resistance here. And you can look up, if you just look up, you know, default units in Neuron. If you ever are curious about, you know, what units are these coming in, because you say you've looked in the literature and you see that, oh, I can see that the length of this soma is in, you know, X number of, you know, units. And then you say, okay, well, I need to make sure that I'm converting correctly. So just be aware that that's, I think, like the first Google hit if you look default units Neuron Yale or something like that. Okay, so similarly for the rest of them, so for the SWC file for the BS02841, anybody find the length and the diameter of that? This one was a little bit, Soma was not the name of the section. It's actually Soma_0. That is something that you'll see, and you can actually just rename that to whatever you want. Kind of standard Python dictionary, in the standard Python dictionary sort of way. Just change that key. Okay, so the length of that was around 39, diameter around 12. And so, you know, I could go through the rest of these, but it's the same sort of idea. You're just going to want to explore, you know, through this dictionary, make sure that you can find the geometry. Any questions there?
I had a question about, are you able to like access, so we're seeing here the length and the diameter and all these other parameters. If you wanted to directly access like L, like the length, you can go ahead and put brackets like L in parentheses. What if you wanted to access length and diameter like simultaneously and like have that in like an ordered list to change? Is that something you can do, or do you have to do one at a time?
So I believe for the output, you know, if you're just talking about just entering the Python command, you know, and then having it come back, I believe you do have to just do that twice. You can make this shorter. You could always call this, you know, you could define this. So say you wanted to say geometry, you know, or geom TC equals this, you know, and then that would make it kind of easier, because then you could just say, you know, what is this? And it could give you that. So, you know, you can do that. But I think for what you're asking, yeah, you would just have to go through and access those values individually from the dictionary.
Okay.
Yeah. Any other questions there? Okay. So then just another exercise. So listing all the channel mechanisms in the Selma compartment of the thalamocortical cell. And just let me know what you guys get. So unless anybody wants me to stop, I'll just go through. So this is just the way that you would do that. You're just looking in the section, looking in the Soma. Mechanisms is where you're going to find mechs, is where you're going to find the channel mechanisms. So that's going to just be the different currents that are at play in this particular compartment. And then it's going to give you these things. And these are not always legible right off the bat. And so, again, apologies if you guys know this already, but so the way or where these come from is these are the suffixes that are defined in the mod files. So it's not always going to, in this case, CADAD, this is a calcium decay mechanism. This does happen to be the name of the mod file, but that's not always going to be the case. So like IA is the suffix that's defined in TIA.mod. So sometimes, and ITTC, so that is, I believe it stands for the T-type current in the thalamocortical cell. So sometimes you may have to open up these mod files, and if you're saying, okay, which, you know, what currents am I even looking at? What did these people put into this particular cell compartment? There's things I want to take out, things I want to put in. And so in that case, you may have to open up the actual mod files, look for the suffix that matches these, and then read the description that the person hopefully left, either, you know, in the paper or in the mod file itself or anything like that. And PAS here, passive, that just kind of comes with the territory, that comes with Neuron. That's not a mod file that you need to download like the rest of these that are listed here. So any questions with respect to the mod files, the suffixes, channel mechanisms, anything like that? Okay. And so now just wanted to be able to change the values of a channel parameter. So say, you know, again, the whole point of being able to import these externally defined cell models is that sometimes you're going to want to change them for your own purposes, to be able to use them, say, because you're modeling a different animal, you're modeling a different brain region, something like that. And so, or at a different temperature, and it messes everything up, which does happen. So you're going to want to be able to change the values of some of these parameters. And so, you know, just let me know if any of this is confusing. Again, we're just going through saying, okay, which channel parameters are in here? Say I want to look at the leak channel. Say, okay, what parameters do I have access to in the leak channel? E and G, these are generally going to be, you know, the reversal potential and then the conductance. And let me know if there's any questions or comments there. There's sometimes going to be other things. Sometimes it'll be G max, you know, it'll change. And again, if you are wondering what a particular parameter is, you may have to go into the mod file itself, and hopefully it's documented, but if it's unclear, you may just have to look at the actual equations and kind of, you know, plot them and see what certain parameter is actually doing. So in this case, if we want to change the conductance of a leak channel, say the cell that we're importing, it's firing too much for what we want, and we want to kind of calm down a little bit, we may want to increase the conductance of the leak channel, so that way it's not as excitable. And so, you know, you can look at the value here, and if you wanted to change the value, you could just say set it to this, and, you know, and then next time you check this, it should reflect the updated value. So any questions there? And that can be very useful. Again, say if you have a particular cell and you're optimizing it, you know, or you're changing it. So let's see. Okay. Okay, great. So it looks like Joe got that file to load. Okay, so any questions with respect to changing channel parameters with mod files, anything like that? Alrighty. Okay, so then this was just an exercise in the same thing, changing the conductance of the leak channel in the Selma of the reticular cell model. Feel free to go ahead and do that. And also, and let me know if there's any questions with respect to that, but it's the same as this. You're just going to find, you know, the Selma compartment. You're going to find where the leak channel is. You're going to find out which parameter represents its conductance, and then you're going to change it. Okay, and so I won't go too into that. The next thing would just be, so say we have done what we've done here, and we have imported just a pure morphology file, so just an SWC file, and we want to be able to now insert channels into it because we want to take it from just a morphology file and turn it into an actual model. And so what might be I'll give you guys just a minute to, you know, what might be a way that we are able to do that. Relatively simple. We'll just go ahead and put in an example. All right, so if everybody is good with that, I'll just put in, say, an example here. So we're just going to do pretty much the same thing go into this dictionary, find the Selma compartment, find the mechanisms, and we're going to just put this this passive mechanism in here, and we're going to say what the conductance is and what the leak or what the reversal potential is. And that should make it into there. And again, you can check that by going ahead and, running that line just without the equals and just making sure that you're getting what you want to get. And again, this is with passive, but you could do this with, with the other mod files as long as you've compiled them already. And instead of, just use the suffix that's appropriate to the channel that you're trying to add, and then make sure that, you also use the parameters that are appropriate for that. It's not always going to be G and E. It's going to really depend on the mod file. So make sure you're using the parameters that are appropriate to that, and then that should take care of that. So let me know if there's any questions or comments with respect to inserting channels into compartments for a pure like SWC morphology file or anything related to that. Any questions there? Okay, so the next one is just going to be to change the capacitance of all the compartments in the model that's defined by this. Oops, sorry, I meant to say the SWC. My bad. Let me change that. Okay. All right, so for this, you can just go ahead and just create a for loop. So we can loop through, that's one of the beauties of having a dictionary. You can go through and you can loop through these sections like so. So we're going to, we can say for sec or section, in netparams.cellparams, you're going to access this particular cell that's already been imported into your cellparams object. And so for all the sections that are, in this part of the dictionary, and then if we want to change the capacitance, and as you may recall from earlier, capacitance is located in the geometry key. So like this, you can just go ahead and run that. So then now, if you were to go ahead and you were to look at every single section in this SWC file that prior to this was just a morphology file, you should see that now each of those compartments should have a capacitance associated with that compartment. So any questions there? Alrighty. So now I think it's 5:53. Okay, so let's just go through this next thing. So the next thing is just to illustrate how making these changes can affect the cell's behavior. So what we're basically going to do is we're going to create a population of these thalamocortical cells. We're going to stimulate it, with some hyperpolarizing current just to see, how does the cell behave. And then we want to go ahead and change a parameter and then see how does the behavior of the cell change in response to that. So the first part of the exercise, so go ahead, just take a minute, create a population of these thalamocortical cells. And I will post how to do that in 1 second. I'll give you guys 20 seconds or so. And again, feel free to interrupt. Let me know if there's any questions. All right, so just the way that we create a population. So it's netparams.popparams, so I believe you guys have seen. So I called this TC pop, so this is just thalamocortical pop. This is an instance where this is arbitrary, and we will, similar to how we discussed before, say if we're going to stimulate this population, we will use this later. But you can call it whatever you want. Thalamocortical pop is what I called it here. And then here we're going to have the cell type specified, the number of cells, and then the cell model. And so this is where the things that we defined earlier are going to matter. So we're going to want to make sure that, say we want to use, one of these cells that you've imported from earlier, the cell type here has to match the cell type from earlier. The cell model here has to match the cell model from earlier. So that way, popparams knows which cells in particular to make that population out of.
But Erica, so why would you even specify the cell model here? Why can't you just create a population based on cell type?
So suppose that you have, so that's a good question. There can be different there can be multiple different cell types that kind of use the same sort of cell model. So say I'm making a model of a cortical column or something like that. And some of these cells are more detailed, they're more full morphologies, and some of them are going to be reduced. So this is actually true for this particular thing. And so we used cell model, the HH reduced, to indicate, okay, these are the populations that are using a reduced version of this Hodgkin-Huxley model. So they're smaller, the morphology is more simplified, and then we used HH or HH full to indicate the ones that were more, that had a more complicated or complex morphology. But the cell types differed, so it would be thalamocortical or reticular, or other things like that, and that just allowed us to kind of keep that organized. In terms of, you're saying why bother to do that even? Let me think. I know that there's a good reason.
No, I guess if you've got one cell type, can one cell type have multiple cell models? Because then that would be
no, not the other way around. So I would say that the cell type should be specific to the particular cell type that you are using, whereas the cell model might be able to be redundant between multiple different ones.
So then, what would you gain by giving the cell model here?
I know that there's a reason that cell type
yeah, so you might have the same cell type using two different cell models because you really want it to be the same type, but one is morphologically detailed and one is highly simplified.
Yes.
So it would be the same cell type, but then under cell model, you would have detailed or simplified. And that way they're treated the same in NetPyNE.
Okay, yeah. So it's Joe brings up a good point in terms of how they're treated. So say you want to do something to a particular group of cells, and you want to do them only to the excitatory cells, or only to the ones that are morphologically simple, or only to the ones that are morphologically complex, but you don't want to go through and have to specify each and every single one. That way you can kind of make a group of, okay, the ones that are the cell model complex, cell model simple, or conversely, cell type, we want to do it to all the thalamocortical cells, whether or not they're the simple or the morphologically complex kind. So it kind of gives you more flexibility in terms of that.
But if I create a population now where I don't specify HH reduced, so if I don't give it a cell model at all here, it's going to default to include every single cell that has the cell type TC, irrespective of the model, right? So if it has multiple models, it's going to get confused. Yeah. It's going to give me an error, and it's going to say, well, what do you want me to do here?
Sorry, say the last part again. If
I did have if I had an HH reduced and an HH model within my TC cell type, then if I didn't specify the model, then it's going to say, well, what do you want me to create a population of?
It's either going to do that or it's going to do all of them, but I don't.
Or it's going to go a mix. Okay.
Yeah. But I don't think that. I believe that you're correct that in terms of the population, in terms of pop params, I do believe that you would get an error, because if you look up here, that's what the conditions are for, and this can actually be kind of a pain sometimes when the condition list is long and you forget to add a condition into the pop params, and then the conditions here are the cell type and the cell model. And so then when you are, specifying the pop params, if both of these have been entered into your conditions list, then it's like, well, it's conditional on those things. So you're going to need to specify all those. Another example might be if, again, we can go back to the example of a cortical column. Say you've added into this condition list a range of the Y values. So like basically where in the column it is. And you're saying, okay, Y norm, the normalized Y value of where these cells is going to be in the bounds of layer 2. And so that way, then when you go down here and you try to create a population, let's see, where was I? If you try to create a population and you don't specify that Y norm range, that kind of where the Y is, then you won't get an error, but it just won't create a population like you're hoping it will. So anything that's in the conditions up here, if you want to, so say your cell params, you have that list of conditions. If you want to create a population from that cell, you have to specify all the things that are in the conditions list of your cell params.
I mean, it hasn't given me an error because I forgot to specify it, but
it might not give you an error, but then if you try to do something to it, you might, like, say if you try to give it a stem or source, you try to give it a current clamp, you might end up with a blank plot because it might not actually, it might be like, okay, well, I created something, but it doesn't have any cells in it.
Yeah, okay.
So that's my bet as what would happen. But feel free to go ahead and test that. And
that makes sense.
Yeah. Alrighty. Let's see.
I have a question.
Yeah.
How in the case of the TC cells, we are able to find out what are the cell type in the cell model? Because for the TCs, we imported from a JSON file.
Mm-hmm.
And in the command, we only set the label and the file name.
Yeah.
We didn't.
So for the JSON files, a lot of these, again, these are going to be slightly different than the HOC and the other files because the JSON files, at least the ones that I have encountered, are usually going to have been saved from a pre-existing NetParams script. So say somebody has created a network and they're like, I want to save all of the cells that I used in this network. You can save them as JSON files, and there's ways that NetPyNE allows you to do that. And then so the cell type and the cell model are actually already listed in the JSON file. So if you go ahead and you just open up that TC reduced JSON file that's in the directory there, you'll actually see at the beginning, you'll see that the cell type and the cell model are listed. So we didn't need to say that for this particular .json file because that was already in that file. But for the .hoc and the .py files, those are not being created in the same ways. And so those are things that we have to add in ourselves versus this JSON file, though that's being saved from a pre-existing NetPyNE script. And the reason that that can be useful is say that you're running, again, I'll default back to this example of a cortical column. You have this huge network and you want to be able to, you don't want to have to create your cells every single time. You don't want to have to be able to load the HOC file, then specify, cell type, cell model, the conditions of where, in terms of the y-axis, the depth of this column, where those things are. So it actually makes it computationally a little more efficient to just be able to say, okay, I'm going to just save all that information in a JSON file. Then I can just load that in every time, and I don't have to spend the energy reinstantiating those populations. Does that make sense?
Yeah, thank you. But for now, for this exercise, how could we in this case, to write the cell type and the cell model, we must open the JSON to get this information.
You could open the JSON file to do that, and you could also explore.
Okay.
Yeah.
Thank you.
Yeah, no problem. Okay, and so the next part of the exercise is just going to be adding hyperpolarizing current clamp, and I suggested a stimulation of -0.1 nanoamps to this population. And so that takes a couple of lines. And I'll just put this first one here since it's already 604. I'll just kind of go through this. So the first is going to be your .stim source param. So this is going to be the source. That's where you're going to specify, what type of stimulation you'd like to give. So I said iClamp for current clamp. This is going to be the delay. So at what point in the simulation do you want this to start? And then the duration. So I want it to go on for, arbitrarily I picked 800 milliseconds. These are in units of milliseconds. And then you have the amplitude. And so this is in units of nanoamps. This is important to keep track of because a lot of stuff in the literature, you may see stuff in picoamps. So just keep that in mind that picoamps, might be out there, but this particular thing is in nanoamps. That's how you define that. And then you can give the target, again, just for the sake of time, do this. Oh, oops, what did I do? Okay, so my bad. Netparams. Oh my God. Yeah, so for this, again, so input your target params, then you're going to put the population that you want to target. And so that in that case, it's the TC pop here. Your source is going to be the input that you specified earlier. You're going to specify the section name that you want to send this current clamp to send the stimulation to. In this case, I'm picking the Selma. And then the location on that section, so 0.5, that's going to be the middle. And then the conditions here. And this is going to, again, this is conditions not necessarily for the cell params, but for the pop params. So the conditions of this are that the population has to be this thalamocortical pop as defined here. So if I accidentally wrote, if I forgot this underscore, it wouldn't stimulate, what I'm hoping it would. So make sure that this name matches, the name that you gave it up in pop params there. So that's how you can do that. And then you want to add your config params. So duration, you have the internal time step, verbose, whether or not you want it to output detailed messages or not. Then you have record traces here. So again, I'm naming this v Selma, so the voltage of the Selma. But then these things, the section name, location, and then the variable, which is going to be voltage. The recording step, it's good to keep that as the same as the time step, not always, but usually. And then a file name, if you want to save as a JSON file, I put false here. And then plot traces. I believe you guys have been over this. I'm going to save a figure. And again, let me know any questions if not. And then here, specifying the temperature. And that is something that's very good to pay attention to, because sometimes you will, again, in this particular case, the whole point of these hands-on exercises is that you're importing pre-existing cell models. So sometimes, people are modeling things in slices or in vivo, in different conditions. And so that can really, really change the behavior of these cells. So if, something looks really strange compared to what it looks like in the paper or something like that, it can be good to pay attention to the temperature that it was run at. And so do this, then we're gonna create the network, just the single cell, and run the simulation. So we have, these. Oh, I have a syntax error. What did I do? Come on. Is everybody else also getting this same error? This literally just worked a second ago. What did I do?
Erika, excuse me. If you could
Yeah.
save this notebook so we could copy and.
Yeah, no, for
go
some
along.
reason it is not allowing me to save. I'm realizing that is an issue right now. It's giving me an error. Not sure why.
Try saving a copy and then using that.
Sorry about this, guys. Yeah, I'm really not sure why it is. Okay.
Where's the error?
It's just telling me that it's down here. So it's instantiating this. Seems like it's working fine. And then I get some type of shape error here. I assume maybe I changed something during one of the exercises up here. I'm just writing it again in this copy that I made. Many apologies. Are you guys able to copy and run this from a copy? Is that because I've been told that's the standard way you guys have been using these collabs?
Yep, I was able to run it.
Okay.
I haven't done all these changes that we did, so maybe that's the problem.
Yeah, I made changes and I can't run it, but I may have done something else wrong.
Let's see, I know this. Okay, so I do get, when I make a copy of it, I'm able to see the model output traces picture that gets plotted. So maybe, let's see. Trying to see if any, all I did was I just imported from NetPyNE so I went to the start of number 2, just redid, importing specs and sim from NetPyNE, loaded the TC reduced file. And I didn't import any of the rest of them. Not that that should make a difference, but just didn't do any of the rest of those. And then let's see. Then I didn't, run any of the exercises here this time. And I tried all this beforehand. Sorry about this, guys. And then I created the population. So then I went all the way down to creating the population of thalamocortical cells. So netparams.popparams. Then I did the stim source, stim target, config, and then ran the network. And then I get the expected output. So again, that is just going up to the start of number 2, importing. And you can maybe restart this and try it, make a copy. So from NetPyNE, import spec sim. Load just that first one, the 2A, so just the TC reduced JSON file. You can skip all the other ones, and then you can skip the exercises, go down, and then to the exercise where it says create a population of thalamocortical cells. Just create that population, netparams.popparams. Like so. And then, yeah, so you guys should be able to see. Yeah, so then this line, this line, this line. And then config, and then this, and it should work. So let me just restart this. And let's see if I can get this to, okay. Let's just start from number 2 in this copy, the original. Okay, I gotta go back to the very beginning. Apologies, guys. Is everybody able to get this, or this is
I did go over to the new copy. So I was working on my own. I had a similar issue you had with the shape, but then I just reran everything and it didn't happen.
Right. Yeah. So I'm not sure which of the exercises caused that issue, but clearly it was probably something stupid. Maybe when I said geom equals, that kind of thing that I did on the fly there, like that might have actually done it. So not entirely sure. Okay. Alrighty. Make sure that works. Yeah, okay, so it's in there. So now that I've imported the TC file, so I'll just skip all of these. I'll go right down to the population parameters line. Go down to here, get this, step my stim source params, my target params, run my config lines again, and then let's see. All right, so here we go. It's actually acting a little strange. Or did I already change it in this one? Okay, so this is actually different than it's supposed to look. I'm going to start sharing this tab with you instead. Apologies.
Yeah, I'm able to see the rebound burst that is intended.
So this is what it should actually look like.
Mm-hmm.
So that was what happened when I just made a copy of this. Again, probably in the midst of some of the exercises, something got changed, and you know, and I don't have the time right now to go through and debug whatever it was that happened there. So I think probably the easiest is just to make a clean copy and just to, you know, just import spec.sim from NetPyNE, import the TC JSON file, instantiate a population of just those thalamocortical cells, do the stem source params, the stem target params, and then the config lines, and then run the simulation. And so you should see something like this, which is a rebound burst. So that happens because we gave it a sufficiently hyperpolarizing current input. And so basically the next part of this exercise was just to set the conductance. So this is usually some, you know, if you may know this, maybe all of you. So typically when we see rebound bursts, a lot of the time that is, especially in thalamocortical cells, that's attributed to the T-type calcium channels. So those are low threshold channels. Basically, they're, you know, a lot of you may have learned about the D inactivation, things like that. Feel free to ask, you know, or look it up. It's a cool little mechanism. And so basically, I wanted to just show, you know, if we set the conductance of the T-type channel to 0, you know, what happens to the cell. So we can go ahead again. I'm going to just start on this clean copy here, and just for the sake of time, because it's already 6:17. So the T-type channel here, the mechanism is ITTC. And again, that's not something that you would necessarily know offhand, especially if this is someone else's model or, you know, from somewhere else that you are importing. You may have to, again, go through the mod files, look at the descriptions, you know, see what the suffix is that you want to use. So in this case, you know, we would go through netparams, .cell params, go through all the way to the mechanisms, ITTC. Gmax in this case is going to be the appropriate parameter for this. We set that to 0, like so. Okay, and so then I'm just going to, just for the sake of clarity, make a new population. I'm going to call this TC pop 0, just to, you know, give us something new to work with. Again, I'm just going to, let me just run these again because I'm now shaken by the what happened before. Okay, so this is, again, I'm just setting the stem source params and the stem target params. I use the same line for the input, you know, for the stem source params. For here, I did change the name of the target to match the name of this new population. And again, oops, that's important there too. So make sure that your population matches what you specified up here. Okay, and then so again, I'm just going to run my config lines, and then I'm going to cross my fingers on this, and hopefully this this works correctly. Yeah, so now we see that rebound burst has gone away, and that's just a dip. It's starting. We could change this by having it start lower using via init, which I believe you guys saw earlier. That's just changing because, again, the T channel is going to have an effect. But as you can see, once it reaches steady state, you know, we give it this negative stimulation, and we can see that there's no rebound burst. So that's just, you know, kind of a quick example of, you know, how we can take these models that maybe, you know, other people have written, other labs, and we can adapt them for our own use, whether that's changing the geometry, that's changing parameters of the electrophysiology, and, you know, just be able to use that for our own projects and things like that. So there's kind of an overview there. And if anybody's interested, again, I'll start wrapping up because I ran a little over time, but there's just a few other things. If you wanted to, say, plot the morphology of a particular cell and make sure that it got into NetPyNE okay, I just put in some commands here. So I'm going to make a population of those Hoax cells that were just morphology. I'm going to run this again. And then this is the command that, this is a command that you can use to plot the shape of a particular cell. So plot shape. Oh, God, no, I need to do matplot inline, don't I? Ay, ay, ay. Okay, and that's not working. Isn't that magical? Okay, well, that was working on the other thing. I'm so sorry, guys. So let me just see if it works on the old one. Okay, well, it was. And this is working locally on my machine, I just checked. Okay, so those are the commands. You can try them locally, and again, I'll try them, and I'll post in the general channel if I see anything other than that. For this, I noticed that this is a Matplotlib error, so there's something to do with this. I think I need to download the older version of Matplotlib for it to work in this collab environment. But either way.
Yeah, we had that same crash in my last session. I think it must be a change in Matplotlib that we need to adapt to.
Yeah, I think, yeah, Robert had suggested using an earlier version of Matplotlib, and I believe that worked. So, but it works on my local machine. Probably I haven't upgraded Matplotlib, that might be why. But so if you try this, just be aware this is not an error. This is not a NetPyNE error. This is a Matplotlib error. But this is the command that you would use to plot a 3D cell shape. Apologies that you can't see it here. And then I was just going to go through kind of making a network, which again, I will talk about more even tomorrow, just setting the geometry of that. And I believe Salvador, I believe I heard him going over propagation velocity and length constant there, and then establishing populations, synapses that we'll use to connect these populations, network stimulation, connectivity rules, and then, just running some simple analysis functions just to plot the 2D representation of your network with connections. And again, this is mostly available on the tutorials that are on NetPyNE. These are just very slightly adapted. And so I will post that link as well. Let's see. Yeah, so this kind of just took pieces of different NetPyNE tutorials. So tutorial 5 is position and distance-based connectivity. Tutorial 6 is adding stimulation to the network. So this was just sort of modifying that and applying it to these new cells that you've imported from these other sources. So that's just kind of a quick and dirty overview of that. And any questions before we wrap up? Alrighty. Well, yeah, so it was great talking to you guys. I will be giving a talk tomorrow in the morning about building data-driven multi-scale models, and then I'll see you guys again on Monday for a talk on our auditory cortex model. Alrighty. And if there's any other questions, feel free to reach out in Slack. All right, thanks, guys.
Thank you very much.
Thank you.
Thank you.
Thank you.
Thanks, bye.
Thank you, bye-bye.
And Joe, I think I might need your help for stopping the recording.
Yeah.
Eric, thank you so much. I saw the ending there. It was fantastic.
Okay. Yeah, just in time for none of my code to work. Great.
But Joe told me the rest was amazing.
Well, yeah, well,
Okay, I'll stop the recording here. Thank you so much.
Yeah, thanks, Selma. Thanks, everybody.